Assalamualaikum warahmatullahi wabarakatuh. My name is Hakimi bin Khairul Anwar, and now I'm going to speaking to you today about the trio of conduction, convection, and radiation, which are three fundamental processes of heat transfer that occur in various physical systems. Okay, the first part is the conduction. The definition of conduction is the transfer of heat through a material without any movement of the material itself. It occurs primarily in solids. The mechanism in conduction, heat is transferred through a material by the vibration of atoms and molecules. Hotter particles transfer energy to neighboring cooler particles, causing them to vibrate and transfer the thermal energy. For example, when one end of a metal rod is heated, the heat is conducted through the material, and the other end of the rod becomes warm.
A very good day to Dr. Azwan and to my fellow groupmates. My name is Stephen Hoylin, and today I'm going to talk about our first experiment for this group project, which will show the phenomena of conduction in heat transfer. For this particular experiment, the apparatus that you may need are steel spoon and wooden spoon, butter, infrared thermometer, thermocouple, and container filled with hot water. The next video will show the procedure of the experiment.
Boil some water using the water heater. Pour the hot water into a container. Measure the initial temperature of the hot water by using the thermocouple. Measure the initial temperature of steel and wooden spoon by using the infrared thermometer. A pinch of butter is placed on the top of both spoons to show the melting process. Soak the end of the steel spoon and wooden spoon into the hot water inside the container and start the timer. For every 2 minutes, record the temperature of the steel spoon and wooden spoon.
One eternity later.
Observe the spoon. Butter on steel spoon already melted, while wooden spoon still not melt.
After conducting the experiment, the data obtained are represented in the table as shown. As you can see, the initial water temperature is 85 degrees Celsius, while the initial temperature of both steel spoon and wooden spoon is 27.8. When it reaches 10 minutes, the temperature of steel spoon is higher than the temperature of wooden spoon. Initially, the steel spoon and the wooden spoons are at the room temperature, which is 27.8 degrees Celsius. So once they are soaked in hot water, the temperature started to rise for every 2 minutes. Why? The hot water molecules at the point of contact with the spoon start transferring their energy to the nearby particles. So in this case, in this experiment, it's the spoon particles. And both spoons eventually warms up, but at a different rates. So as you can see in the data obtained just now, the steel spoons, it has a higher temperature, it has a higher final temperature than the wooden spoon. So of course, after 10 minutes, the butter on the steel spoon melts faster than the wooden spoon. This figure shows the graph of temperature of both spoon versus time. And as you can see, both spoons started with the same initial temperatures. However, at the final temperature, the temperature of steel spoon is slightly higher than the temperature of wooden spoon. Based on the graph, we can conclude that the steel spoon is an excellent conductor of heat. As soon as it touches the hot water, the heat quickly travels through the metal. However, wood, being a poorer conductor compared to steel, transfer heat more slowly. When the wooden spoon is placed in hot water, the heat takes more time to spread through its material. And as the temperature is being recorded in every 2 minutes, it can be observed that the steel spoon's temperature rises rapidly because of the effective conductions. On the other hand, the wooden spoon's temperature increases more gradually due to the slower conductions of heat in wood. And that is all from me. Thank you.
We'll meet again. Okay, now I will explain to you about the theory of convection. The definition of convection is the transfer of heat through the movement of fluids. in brackets, liquids or gases. It occurs in fluids where there is a bulk movement of the substance from one place to another. The mechanism convection involves the circulation of the fluid due to the temperature differences. Warmer regions of the fluid become less dense, rise, and are replaced by cooler, denser fluid, creating a continuous flow. For example, boiling water in a pot is a common example of convection. The heat from the bottom of the pot causes the water at the bottom to heat up, rise, and circulate while the cooler water descends.
Good day to Dr. Azwan and my fellow friends. My name is Lavindra, son of Srinivasan from Section 1, and my metric card number is CT210255. And today I'm going to talk about our second experiment for this group project, which will show the phenomena of convection in heat transfer.
Pour 3 different temperatures of water in the cup. Hot, warm, cold. Add a few droplets of green food coloring in each cup. Add a few drops of red food coloring in the water in each cup.
A few moments later.
Results of dissolving food coloring in each cup of water. After a few minutes.
So basically, this is our apparatus for the experiment of convection. First is it shows that the kettle that it consists of hot water. Second is warm water with a room temperature. Third is cold water, and the fourth is a clear container. We have three number of clear container. Fifth is food coloring, consists of coloring, which is two colors, red and green, and the last one is steel spoon. This slide shows the result of our experiment. This is a picture of our experiment taken after 10 minutes. As you can see, for the hot water molecule moves very quickly compared to the other two containers. The color acts mixed and it's already dissolved with the hot water. Where the warm water takes the molecule takes a little bit to dissolve with the normal water, where the cold water isn't moving at all, and it takes more time to mix with the solution, and takes long to dissolve. As we know, we can say that the hot water molecule are more faster in the room comparing with room temperature and the cold water. Now I will talk about the discussion. Hot water dissolution. In the hot water scenario, the rapid dissolution of food coloring can be attributed to increased molecule movement and kinetic energy at a high temperature. The heat energy supplied to the water molecule enhance their ability to break down their molecule bonds of the food coloring, leading to a quicker and more thorough dissolution. Warm water dissolution. The observation that food coloring take a few minutes to dissolve in a warm water aligns with the expectation that temperature plays a significant role in solubility, while the warm water facilitates faster dissolution compared to a cold water. It requires more time than the hot water due to take a lower temperature and, consequently, lower molecule activity. Lastly, cold water. The cold water dissolution. The prolonged time required for food coloring dissolve in the cold water is indicative of, of the impact of the temperature on the solubility. In a cold water, the kinetic energy of molecule is lower, leading to reduced molecule movement. As a result, the process of breaking down the food coloring molecule is slower, requiring an extended period of time. Thank you.
Okay, the last one is radiation. The definition of radiation is the transfer of heat through electromagnetic waves, such as infrared radiation. Unlike conduction and convection, it can occur in a vacuum where there is no medium to transfer heat. The mechanism in radiation, for example, heat is emitted in the form of electromagnetic waves. These waves can travel through empty space and do not require a material medium. Objects emit radiation based on their temperature. One example of radiation is the heat from the sun reaching the earth is a form of radiation. Objects like hot stovetops also emit infrared radiation.
First, make sure you've got your trusty metal spoon ready for action. It's the star of the show. Prepare other apparatus like oven, mitt, and oven. For measurement, we will use digital thermometers. Next, we need a preheated oven, set at around 350 F175C. Take initial temperature of the spoon. Take metal spoon and gently place it inside the oven. Notice how it's not in direct contact with any flames or heating elements. After 30 seconds, take temperature reading on spoon. Repeat this step for every 30 seconds.
As for this experiment observation, which is heat transfer by radiation, as the oven heats up, keep a close eye on the spoon. You will notice that it begins to get hot. But why is it happen? This is where the magic of radiation heat transfer comes into play. As you can see on the video, even though the spoon is not directly touching any hot surface, it's absorbing heat through radiation. The hot walls of the oven emit infrared radiation, and the metal spoon absorbs this radiation, causing it to heat up. This phenomenon is a classic example of heat transfer by radiation. Before we dive into the data, let's set the stage. We have recorded the temperature of the spoon at regular interval throughout the experiment. Now let's plot those data points and analyze how the temperature changed over time. This is the graph that we have obtained from this experiment. As we can see here, on the x-axis, we have time intervals, and on the y-axis, we have the corresponding temperature of our trusty spoon. Let's dive into the analysis and see what insight we can gather. You can see on the plotting graph, at the beginning of the experiment, the temperature of the spoon was relatively low as the spoon absorbed the initial radiant heat. As the time passed by, the temperature steadily increased, showcasing the ongoing process of radiation heat transfer that happened in this experiment, which is the heat transfer from the oven to the spoon. The interesting pattern that we obtained in this graph, we can conclude that the temperature is increased linearly over time. Okay, now let's not just observe but quantify our finding in this radiation of heat transfer experiment. As you can see, we can use the formula for the heat transfer, which is Q equal to mc multiplied by the differential change of temperature of the system, which is Q is amount of heat supplies to the system, which is our system is spoon, mass of the system, and the C is specific heat capacity of the system. As you can see, the C of metal, which is 0.5, and mass of the spoon is 0.035 kilogram.
As we crunch the number and sum up this individual heat value for each temperature and time, we arrive at a fascinating result. The total amount of heat transfer absorbed by our spoon throughout the experiment is approximately 0.891 joules. It's obvious that the total amount is may vary for each experiment because of several factors like the temperature of environment. This numerical insight not only validates our qualitative observation, but it also helps us quantify the energy exchange that occur during the radiation heat transfer process. It's fusion of theory and experimentation which is that we implement in this experiment. As we journey through the analysis, we are gaining a comprehensive understanding of how radiation heat transfer function in a real-world scenario. Feel free to explore the detailed calculation in the description. Now, as we have unraveled the mysteries of radiant heat transfer in our spoon in the oven of experiment. During this experiment,
Okay, we already reached to the ending of our presentation. Okay, now I will be explain to you about the conclusion or learning outcomes, what we can get from all three experiment, such as conduction, convection, and radiation. Okay, the learning outcomes of the experiment is that we can understand the conduction, convection, and radiation not only provide insight into the physical processes governing heat transfer, but also offers valuable life lessons and principles that extend beyond the realm of thermodynamics. And summary, the principle of conduction, convection, and radiation not only contribute to our understanding of physical phenomena, but also offer metaphors for navigating the complexities of life. By drawing parallels between these thermodynamic concepts and personal or societal experiences, we can derive valuable insight that extend beyond the boundaries of scientific understanding. Okay, thank you.